I'm introducing another chapter, which is bone development. I'd initially talked of this on our introduction. It's just some additional or advanced information. So starting with intramembranous ossification, this is the development of bonds from fibrous membrane. And the bonds formed by this process are the flat bonds, those of the skull, including frontal, parietal, occipital, and temporal. Also, clavicles are formed by this process. Apart from intramembranous ossification of clavicle also undergoes endochondral ossification. So it has both the two processes. So stages of intramembranous ossification. This begins with ossification center appears in fibrous connective tissue membrane. So the ossification center appears in fibrous connective tissue membrane. Then bone matrix is secreted within the fibrous membrane. Bone matrix secreted within the fibrous membrane. Woven bone and periosteum forms. So the woven bone and periosteum forms. Then bone collar of compact bone forms and red marrow appears. So these are the four processes or the stages that intramembranous ossification undergoes. So just check them on these diagrams, these pictures. So the first one here, we have the mesenchymal cell, the collagen fiber, then ossification center, the osteoid, and the osteoblast right here. So an ossification center appears in the fibrous connective tissue membrane, selected centrally, whereby the mesenchymal cell cluster and differentiate into osteoblast, forming an ossification center. Then crossing to this other side, we have bone matrix osteoid is secreted within the fibrous membrane. Osteoid are here. Then this the newly calcified bone matrix. Then we have the trapped osteoblast becomes osteocytes. The osteocytes are here, and these are still the osteoblasts which are under the process of secreting the osteoid. Moving to this other one, we have mesenchymal condensing to form periosteum. Trabecula of woven bone is here. Then the blood vessel are starting getting into the newly formed bone. So accumulating osteoid is laid down between the embryonic blood vessel, which form a random network. The result network, instead of lamellae, forms trabeculae. Then vascularized mesenchymal condense on external surface. Yes, as shown here, they are now condensing to form the periosteum. Then finally, bone collar of compact bone forms and red marrow appears. So fibrous periosteums are there, then osteoblasts are there still forming bone, then plate of compact bone, the diploid, which is spongy bone, and cavities contain the bone marrow. So you're told that the trabecula just dip to the periosteum, thicken, forming a woven bone collar that is later replaced with mature lamellae bone. Then spongy, the diploid consisting of distinct trabeculae persist, and that we have this plate of compact bone there. Bone formation now, by replacing hyaline cartilage, is known as endochondral ossification, and they include long bones, vertebrae, and hip bones. So sorry for that distraction. We have bone formation by replacing hyaline cartilage, and they include long bones, vertebrae, and hip bones. These bones undergoes endochondral ossification. So we have also stages for endochondral ossification, and the first one being formation of bone collar, the second one being cavitation of the hyaline cartilage, then inversion of periosteal cavities by periosteal pad and spongy bone formation, formation of medullary cavity, then formation of secondary centers in the epiphysis. And finally, we have ossification of the epiphysis with hyaline cartilage remaining only in the epiphyseal plates. So in general term, we have the formation of bone collar, we have cavitation of the hyaline cartilage, Then inversion of periosteal cavities by the periosteal bud and spongy bone formation. Then formation of medullary cavity, formation of secondary centers in the epiphysis, and finally ossification of the epiphysis with hyaline cartilage remaining only in the epiphyseal plates. We'll have a demonstration here, the diagrams to show the same. So we have the hyaline cartilage like this. Then we have a primary center of ossification right here. Then we have bone collar right here also. And this is the first one, which is the formation of bone collar around hyaline cartilage model, the formation of bone collar. The second one, we have cavitation of the hyaline cartilage within the cartilage model. This now, the cartilage model, now we have the deteriorating cartilage matrix, which is the cavitation now. The bone collar is right here, still there, intact. Then moving to the next, we have inversion of internal cavities by periosteal bud and spongy bone formation. Now we have the inversion. As you can see, blood vessel and the within the periosteal bud entering in the deteriorated cartilage matrix right here. Then we have the spongy bone formation. Spongy bone starts form around these surfaces here, like this point. Then moving to the fourth, we have formation of medullary cavity as ossification continues. Then appearance of secondary ossification center in the epiphysis in separation and preparation for stage 5. So this process continues as the bone matrix keeps being secreted and formed. Then we have now the development of secondary ossification center right there. Then we have epiphysis just immediately after inversion of epiphyseal blood vessel. Then immediately there is beginning of formation of secondary ossification center. Then finally, we have ossification of the epiphysis. When completed, the hyaline cartilage remains only in the epiphyseal plates and articular cartilages. So, and that's the case whereby you can find them articular cartilage, whereby this will later form part of joint. Then we have spongy bone, which has eventually developed and is now getting older and older. Then we have the epiphyseal plate cartilage, which is this, and keeps narrowing time to time until it fuses in older stage when ossification completes. So this is the summary of stages of endochondral ossification. So bone growth and remodeling. How the process of bone development, still there is a need of remodeling too. So, and what are these part of bone remodeling? So we shall start with this. Bones growth is by two distinct ways, which is interstitial growth of plates, epiphyseal resulting to growth in length of all long bones, and opposition growth in thickness of all bones. So we have two distinct ways, the interstitial growth and the opposition growth. We're told that interstitial growth of plates, epiphyseal resulting to growth in length of all long bones. So all long bone growth grow in length by interstitial growth. Then in thickness, we have opposition growth, and that's for all bones, not only exclusively for long bones, but all bones. So under opposition growth, this is the growth in thickness of bones by deposition of bone matrix by osteoblast beneath the periosteum. So we have the periosteum underneath. Okay, the periosteum which we have been talking about, which has the osteogenic cells, now will secrete osteoblast, which will now build up the bone and it will grow along with thickness. So the bone will become thick by being deposited with new matrix. So the other one is interstitial growth or interstitial growing. This is the growing in length of bones occurring at the osteogenic zone through the rapid division of the upper cells in the columns of chondrocytes. Chondrocytes are the cartilages, so the cells forming the cartilages. So calcification and deterioration of cartilage at the bottom of the columns and subsequent replacement by bone tissue. So this is something which keeps on growing. So starting from this, let's use this diagram here to describe the same. So interstitial growing. So we have the resting or quiescence zone right here. Then we have growth or in bracket purification zone, where cartilage cell undergoes mitosis, that is chondrocyte, the cartilage cells. Then we have hypertrophic zone. These are older cartilage cells which enlarges now. So we have the cartilage cells, they're now getting more big or more wider. So we have then calcification zone. We have the calcification zone right here. After the cartilage keeps growing older, then we have the calcification zone. Then immediately after that, we have matrix becomes calcified and cartilage cells die. Then matrix begins deteriorating around here. The matrix begins to deteriorate. Then ossification zone or ossification zone, osteogenic zone, the new bone forming is occurring. And here we have calcified cartilage spicules right here. Yeah, then we have osteoblast depositing bone matrix right here, immediately here. Then osseous bone or bone tissue covering cartilage spicules. And this is how interstitial or how bone grows in length. It's a series of action. This gets deteriorated, but the other one starts fixing. So bone deposit and bone resorption is called remodeling. So this chapter will be dealing with also bone remodeling on this slide. So for bone, is constantly remodeled by osteoclast and osteoblast. We have osteoblast and osteoclast are performing their function here. So osteoblasts produce new bone and start as a bone lining cells with slender cellular processes that make contact with more mature osteocytes within the mineralized bone. Then osteoclasts are bone-degrading cells produced from hematopoietic progenitors. So then these osteoclasts, upon their activation, they bind, sorry for the spelling mistake here, they bind the surface of bone and secrete enzymes beneath. So now as osteoblasts produce new bone, immediately osteoclast starts to digest where it has been deposited more than required, so that the bone will at least grow on its original shape. So this is just like shaping bone into its normal way, so that it cannot appear as any other regular structure which is not required. So we have the enzyme secreted by the osteoclast, are lysosomal enzyme, digest organic matrix of bone. Also, we have acid phosphatase. You can check from your advanced books. You can find these products. It's also produced that converts calcium salt into soluble form. So we have this basic component in organic form of inorganic component of bone, which is calcium phosphate. Now they are now converted to calcium salt by this acid phosphatase, then into soluble form. And finally, the dissolved matrix is transcytosed across the osteoclast cell, where it's secreted into interstitial fluid, then into the blood. So the bone which has been diminished, it's then transcytosed across the osteoclast cells, whereby it is secreted into interstitial fluid, then into the blood. So that's how remodeling takes place. By this diagram, you can find out that both bone secreting cells are depositing the matrix, while the bone resorption cells are taking over, and bone is remodeled regularly. So we have this, for this case, we have cartilage grows here, around here. This is the cartilage, keeps growing, then becomes deteriorated with time. Then we have cartilage replaced by bone around here. Immediately as cartilage becomes deteriorated, they're immediately replaced by bone cells. Then cartilage grows also here, just at this region. Then we have cartilage replaced by bone around this region. So cartilage grows here. As they grow, they just become deteriorated down to this level. Then bone fix here. Then also the same cartilage grows here. Then they are fixed with bone after being deteriorated. Just as the same, as you can find out that the normal outline of bond is supposed to be this way, and the dots joined here is supposed to be this way. That's how it's supposed to be. So this is elongated bond, and eventually it will be remodeled back to its original shape. Yeah. So bond resorption here, bond resorption here on outer surface and the inner surface, because we have endosteum, you have periosteum outer here secreting the osteogenic cells. Then remodeling supposed to occur. So we have functional hormones in bond remodeling. And the first one, we have the calcium. In the body, it's essential. So calcium ion is in the body is essential in structural development of bones, as well as other major roles as in transmission of nerve impulses, muscle contraction, blood coagulation, cell division, and secretion by glands and nerve cells. So calcium is very important and the essential product for bone, and not only bone, but other vital roles. So when calcium level rises in blood, thyroid gland is triggered to release calcitonin that stimulates calcium deposit into bone. So when blood calcium is taken, then it's realized that the level of calcium is high. Then thyroid gland is triggered now to release calcitonin that stimulate calcium deposit into bone, so that bone will grow on its normal and required way. Falling of blood calcium levels signals parathyroid gland to release parathyroid hormones that signals osteoclast to degrade bone matrix and release calcium into the blood. So this process is simultaneous. When calcium rises in blood, thyroid gland is triggered, whereby it releases calcitonin that stimulates calcium deposit into bone. Then the other side, when calcium level falls in blood, there's need for parathyroid gland to be signaled, so that parathyroid hormone can signal osteoclasts to degrade bone matrix and release calcium into the blood, so that calcium may be at its normal level. We have other hormones that all the same they perform other basic functions, such as thyroid hormone stimulate. The same thyroid hormone stimulates epiphyseal disc closure. Testosterone and estrogen also stimulate plate closure. So that's why when a person grows in length or with age, these are definitely that epiphyseal closure as he becomes an adult. This is an illustration, just an illustration of how this works. So calcium homeostasis of blood is 9 to 11 milligrams per 100 mils. And when this imbalance, whereby calcium level in blood raises, the thyroid gland being stimulated, then parathyroid, then this parathyroid which calcitonin is secreted. Then, however, calcitonin stimulate calcium salt deposit into bone, and finally the balance comes to its normal level. So when calcium falls in blood, the same as applied, thyroid gland releases this hormone, parathyroid hormone, which stimulate or signals osteoclasts to degrade bone matrix, whereby we have calcium level turning to its normal or considered level. Yeah. So we also have growth hormone. These are very essential during growth and development of bone. So growth hormone and insulin growth factor are important regulators of bone homeostasis and are central in the achievement of normal longitudinal growth and bone mass. So these hormones are very basic and of importance. So also we have insulin growth factor and additional information. It enhances the differentiation function of the osteoblast and bone formation. So it enhances the differential function of osteoblast and bone formation. So those are the hormones which play a very important role during bone growth and bone remodeling, and also bone formation. So we have also nutrients that are required for bone growth. From our normal eating or our normal diet, we may find one or more nutrients from this food, and these include the calcium, protein, magnesium, phosphorus, and vitamin B, potassium, and fluoride, which are very essential for bone growth, and also proper bone development. However, there are other several vitamins and minerals needed for metabolic process related to bone. They include manganese, copper, boron, iron, zinc, vitamin A, vitamin K, vitamin C, and finally the vitamin B. So those are the nutrients very essential and very important during the development and growth of all bones. So at least maybe in your diet, you're missing such vitamins, maybe you should try as much to add them so that you can have or achieve your normal bone growth. We'll move ahead to function of bones. And the first one is support. Uh, this is now where bones forms a framework that supports the body and cradles soft organs support. So the bones are the basic framework, they form basic framework for the support of the body that cradles and cradle soft organs. Protection. They provide protective cases for the brain, spinal cord, and vital organs they contain. As for the sake of brain, we have the cranial bone, then spinal cord, we have vertebral column which protect the spinal cord, and finally the vital organs they contain, we have the ribs which protect the heart, lungs, and other organs. Also pelvic, they protect other organs of the body. Movement. So the bones are under movement, they provide levers or muscles, allowing movement of the body as whole and off part of the body by forming joints. So movement comes on part of function of bone. We have mineral storage. Under mineral storage, bones act as a reservoir for minerals, especially calcium and phosphate. So bones are the mineral reservoir for these two salts. Blood cell formation. Production of blood cells, this especially the red blood cell, they're formed within the marrows or cavities by the process known as hematopoiesis. So hematopoiesis is the formation of blood cells from the red blood cell from the bone marrow under that said. So energy storage, yellow bone marrow stores lipid, which is fat and glycerides that can be used for energy when needed by the body. So that's the basic and essential function of bone. So in general, we have those functions: bonds, including that mineral storage, blood cell formation, energy storage, and in summary, they protect the vital organs of the body, movement, and support the function of bones. Just review at least 1 second, then you can be able to analyze and transcode them into your thoughts. In adults, this is just an additional information. Marrow cavities contains yellow marrow that can revert to red marrow when a person becomes very anemic and needs more red blood cells production. So in adults, we have this marrow because as in children or the pediatrics, the marrow is still red, but when a person becomes mature or becomes an adult, the yellow bone marrow now reverts to red bone marrow when a person is very anemic or this less blood in the system of a person. By old age, most of the bone marrow has turned to reddish jelly called gelatinous bone marrow. So when one picks a bone from an old person,